Hello everyone. Today we are going to discuss the last second point called as bond energy and bond dissociation energy. In this lecture we are going to discuss what is meaning of a bond energy along with a bond dissociation energy in a gaseous molecule along with its calculation part. So see here, first bond energy. What is meant by a bond energy? Okay. In a chemical reaction, when bond is formed, what happens here? Energy is released. Energy is released. That is, the reaction is a exothermic one. Okay. What I am saying to you, that is, when a bond is formed between any two atoms from a chemical reaction, so what happens? Energy is released, and as the energy is released, the reaction is called as a exothermic reaction. On the other way, when bond breaking process occurs, at that time what happens? Energy is absorbed. That is, it must be a endothermic reaction. It is a endothermic reaction. Okay. Now according to this criteria, we have to define what is meant by a bond energy. Again I am repeating this. When bond is formed, at that time energy is released, and when bond breaking processes occurs, at that time energy is absorbed. The reaction is called as a endothermic reaction. Now what is the definition of this bond energy? See here. Bond energy is defined as the average amount of energy per mole when breaking of a bond from into its elements from a molecule in its gaseous state. Okay, what is the definition here? This bond energy is defined as it is the average amount of energy per mole when breaking of a bond occurs into its elements from a molecule in a gaseous state. This is also called as bond enthalpy or only enthalpy of formation. Enthalpy of formation. Okay, now see here. Now we have to calculate here along with this bond energy and bond dissociation energy. This is the definition of about the bond energy. Now what is meant by the bond dissociation energy? See here. In case of a diatomic molecule, for example, X2 dissociates into its gaseous state, that is X of gaseous plus X of its gaseous state. Okay, that is the definition of the bond dissociation energy is that is the energy is required to break a bond between the atoms of a molecule when it is in a gaseous state. Okay, what is the definition? That is, energy is required to break a bond between the atoms of a molecule when it is in a gaseous state. That is, this is a molecule. Here there is formation of two atoms. That is, in another words, we can easily say that is the energy is required to cleave the bond between the atoms of a molecule when the molecule is in its gaseous state. Now we have to calculate the bond energy. Okay, for example, I am taking the example. For the calculation of a bond energy, suppose we have the examples like this here. First is H2O gives rise to in gaseous state here H plus H and OH in gaseous state. Here delta H is equal to what here? That is 502.1 kilojoule per mole. Okay. Second reaction is that is OH in gaseous state gives rise to O in gaseous state plus H in gaseous state. Here also delta H is equal to plus 423 kilojoule per mole. Okay. Now, in these reactions, we have to calculate the bond energy. That is the average bond energy. Suppose taking this equation as equation number 1, here equation number 2. Therefore, average bond energy is equal to, bond energy that is equal to delta H is equal to what? That is the sum of delta H1 and delta H2 here. Okay, that is equal to delta H1 plus delta of H2 divided by 2. Here we can take the total here 50.2 plus 1.1 plus 423 divided by 2. What is the total here? I am taking the total 50.21 plus 423 here, that is equal to 1, here 2, that is equal to what? 925.1 divided by 2. Now dividing of this quantity by 2, that is equal to 4, here 6, 7, 5.5, that is kilojoule per mole. That is, the average bond energy can be calculated here, that is equal to 467.55 kilojoule per mole is the average bond energy for this reaction. Again we take the another reaction, that is the formation of a CH4. In this also we have to calculate the average bond energy of a which, that is a H bond here. And in this example CH4, their number of CH bonds are equal to how much? That is equal to 4. And in this 4 CH bonds, we have to calculate average bond of energy per mole. Okay, therefore we have to calculate the energy of each CH bond. Say, let us take the example here. Second example, formation of a methane. Next example, formation of methane. Okay, the reaction is like this here. That is, first reactions are CH4 gives rise to C graphite plus 2H plus H in gaseous state. Okay, second reaction, C graphite gives rise to a C of gas. Okay, third reaction is what? That is 2H2 here, 2H2 here gives rise to 4H in gaseous state. This the delta H1, delta H2 and delta H3 are given as equal to this here, equal to plus 75.3 here plus 716.7 and equal to plus 872.0 kilojoule per mole. Here kilojoule per mole. Okay, now how to calculate this reaction here? That is the average bond energies. How to calculate here? See here, in these reactions, that is the formation of a CH4. CH4 is present in a gaseous state here, gives rise to C graphite plus 2H2. C graphite gives rise to C of carbon of gaseous state, and whatever may be two gaseous states are, there is formation of a 4H. Okay. Now the delta H1, H2 and H3 for these type of reactions are given to you. Now the average bond energy per mole, that is E of, here we have to calculate what? That is the CH bond. That is in the CH4. How many bonds are of CH? That is equal to 4 CH bond. We have to calculate average bond energy. We have to take the total and take its average, that is delta H1 plus delta H2 plus delta of H3. Okay, and from this here we have to take how many of these, that is equal to what? 75.3 plus 716.7 plus 872.0 divided by how many bonds? There is equal to 4 bonds. Therefore we have to take the here divided by 4, and that is equal to the answer, that is equal to what here? That is plus 1664 divided by here also a 4. Okay, now what is the total reaction in this reaction also? That is here 4, that is equal to 4, 1, okay, and 6, that is 416 kilojoule per mole of the energy. Okay, now we have to take only here the, what is the enthalpy change, not a reaction. First we have to write the reaction in this sequence. This is the 416. Now we have to write the reaction here first as like this. First we are taking the sum, of the reaction, that is CH4 gaseous state plus C of graphite plus 2H2 of gaseous state gives rise to C of graphite plus 2H2 gaseous state plus C gaseous state plus 4H of gaseous state. Which terms are going to be cancelled here? That is C graphite, 2H2, 2H2. What is the remaining one here? See here. Therefore, CH4 of gaseous plus, what is the remaining here? That is equal to CH4, that is gives rise to here what? That is C of gaseous state plus 4H of its gaseous state. And the average energy is what? That is E of CH is equal to delta H1 plus delta H2 plus delta of H3 divided by how many bonds are here? Equal to 4 bonds. Therefore we have divided it for a 4. Thus we have the answer, that is equal to what here? Now we have to take this total of this, all the 3 reactions of a enthalpy of the reaction. That is equal to what? Here 75.3 plus 766.7 plus 872.0 divided by 4. This much quantity is equal to what? That is 1664 divided by 4 here. What is the answer here? That is equal to 4, 1, Okay, and 417 kilojoule per mole. This is the energy is required for the each CH bond. But after the dissociation of a CH4 like this here, that is E of CH is equal to what? 416 kilojoule per mole here. But the dissociation of CH4 is at is it CH3 plus H. Here also CH3 is going on CH2 gaseous state plus H. Here also here. Now third is reaction plus H here, gaseous state here. Also here CH2 gives rise to a CH gaseous state plus H, and here also CH gives rise to C of gaseous state plus here also a H here. Okay. Now in these reactions, whatever may be the amount of the average bond energy is not to be equal to a 416 kilojoule per mole. It is maybe of a less than value of a 416, or it is a more than value of a this, that is total is equal to each of a average bond energy is equal to what? That is 416 kilojoule per mole. Okay. Now we have to calculate another point, that is called as calculation of a resonance energy. See here. Already you know that is the calculation of bond energy is from the enthalpy of the reaction. Is from, that is the enthalpy of the reaction. Okay. Suppose in a structure of a compound contains, if a resonating structure, at that time what happens here? We have to calculate first here. In this state we have to calculate first the calculated value of the structure given to you and comparing this structure with a experimental value. This is a calculated value and about this a experimental value. When experimental value is greater than that of calculated value, at that time we can easily say that is here the resonating structure is the more stable structure than the other structures. Okay. Again I am repeating this. If the compound of a structure that possesses a resonating structure than the normal structure, here we have to first calculate of a total compound of a calculated value along its single bond, double bonds. Okay. Then we have to compare it with the experimental value of that particular compound, and if the experimental value is greater than that of calculated value, we can say that whatever may be the difference between the calculated and experimental value, that is the value of a resonance stabilized energy for the particular structure, and therefore the resonating structures are more stable structures than the simple structure. For the simplicity, we can take the example of a benzene here. See here. Structure of benzene. According to a Koch's formula here. See here, what is the structure here? That is, this is the structure of a benzene. It is also is comparison with a structure like this, that is a like this. Now we have to calculate first the value. What is calculated value? For that purpose, we have to write this structure compound in a carbon hydrogen way here. Okay, C and C here. Okay, now how many H are here? That is equal to like this, H, H, and here H. Okay, now how many? Single bond CH. How many? 1, 2, 3, 4, 5, 6. Okay, equal to 6. Single bond between CC. CC is equal to what? 1, 2, and here 3. Okay. Single bond. Sorry, here double bond between CC equal to how many double bond? 1, 2, and here 3. Now, requiring the value of each single bond, that is equal to into 6, each of single bond between CC into 3, and each double bond of a value into a 3. We can calculate the here calculated value here. As here for a single bonds we are given as CH is equal to 6 is equal to what value is equal to? CH bonds is what? Here I am taking this value. CH bond is given to the value that is equal to 416.2. For CC bond 615.0, and C equal to what? That is equal to here C double bond C, and here C single bond C is equal to what? 347.3 here. Okay, these are the values we are given. Okay, that is kilojoule per mole here. Okay, now we can calculate the experimental value here. How many? That is equal to what is? That is CC 3 into CC plus 3 into C double bond C plus 6 into C into H. What is the here answer? That is 3 into CC. CC bond is what is the value? 347.3 here. Okay, plus 3 into C double bond C is what? 615.0 plus 6 into what value? CH 416.2 here. Okay, I am taking the calculation, and here see the calculation, that is equal to what? Here now this is can be written as here again 3 into 347.3 plus 615 into 3 plus 416.2 into what? How many CH bonds are here? That is equal to a 6 here. Ratio as 3 into 3 9. Okay, that is equal to 1 2 8 10. Okay, 1041 plus here also 615 into 6 here, that is 15 into 3 18 plus here 2 is 2 आले, sorry 12 Okay, now what is the total of here? Here 249.7 here, then 1041 plus 1845. Okay, what is the remaining one here? That is equal to what here? That is here that value is equal to 5383.2 kilojoule per mole here. Okay, now what about the heats? Experimental value of the given here, that is equal to what? Here see the here value. Therefore, experimental value is equal to what? that is 5534 kilojoule per mole. Okay. Now what is the value given to you here? That is equal to 5535.0 here kilojoule. What is the difference? The difference in between experimental value and a calculated value is equal to what? 5535.0 minus 5383.2. What is the remaining here? 1 here, 5, 1. Okay, that is equal to what? 151.88. This much extra energy which is required for a resonance energy here. Okay, what is the answer here? The remaining is what? Answer here, that is extra energy is what? That is 151.8 here. Okay, correct answer is, this is the correct answer. That is the extra amount of energy required for resonance, that is equal to 151.8. Therefore, the resonance structure of benzene is the most stabilized structure is 1. In this way, we can here explain the resonance energy, bond dissociation energy, and here calculation of a and definition of a bond energy here. Okay, thank you.